On with Stokes' theorem.
Stokes synthesis.
You wait for the evening out.
So, I do want to make a comment that Dennis stopped after class to observe yesterday, and it was something I wanted to say. So we had, we're saying, without, I'm not writing out all the hypotheses of the theorem again, but Stokes' theorem is telling you that integrating a k-1 form over the boundary of M is equal to integrating its d over M. So what is this telling you if you have two different M's with the same boundary, including orientations?
So the same?
All the same.
dw over m.
All, yeah.
The integral of?
Halfway.
No, no, no. So if M1 and M2, so imagine that you had this as your boundary. You could imagine, for example, this as an M that had that boundary. So now I suppose I should be orienting things to make it clear. So if we go around there, I have to orient my M upwards, as it were, right? But what would be another M I could do?
Big blob.
I could do, I don't know about a blob.
You do like a, you have some room for creativity here.
Yeah, like a chef's hat.
That's right, I could do a chef's hat, or I
Everyone
could
like
do
a-
an obscene glove.
Peace.
It's definitely a blob.
So both of those surfaces have the red curve as their boundary. So what do we conclude from Stokes' theorem?
The integral d omega.
The integral of d omega
over the manifolds were the same.
Can you conclude that the integral of any form over M1 and M2 is the same? Only exact forms. I.e., the integral over M1 equals the integral over M2 for any exact K form. So let's put a phi in there.
So basically, there has to be omega to give you d omega speed.
Right. So what does this remind you? What is this analogous to?
Comes up here.
It's like the fundamental theorem, basically, where we said if you integrate an exact one form, the answer depends only where you start and end. This is the generalization of that. So we're going to see all sorts of physical implications of this very shortly. So we're going to, and I am next week going to talk about how you formulate all of the Stokes theorem stuff in classical notation and physics interpretation of it. But this is saying, basically, if you're trying to compute the integral of d omega, and you don't know how to compute this side on the boundary, but if you were trying to compute this, you are free to choose any m that's convenient over which you can integrate d omega, and you'll get the same answer. So if someone handed you, for example, this weird glove-shaped thing and said compute the integral of d omega over it, you could say, oh, well, why not just change it to make it this green thing, which is so much easier to integrate d omega over that. Okay? So this has, you can probably guess this is going to have some good physical consequences. Mm-hmm.
Alright, this might be a, no, this might be a dumb question.
Why don't you just say it?
Is there a generalization of Stokes theorems for like non-manifold regions?
Within reason, yes, but not totally generally. So I already made the comment that we could, that we're not allowing manifolds with corners, but the theorem's still gonna work even if boundary M has corners.
Is it wrong to kind of assume that, I just keep thinking like path independence,
That's what I said 5 minutes ago.
but how do you, like, can you have path independence for like a manifold?
This is the generalization
Okay.
exactly of the statement that if you took an exact one form, df, the integral depended just on the endpoints and not on the particular path. This is the generalization. Okay, so, all right, on with examples. So, suppose I give you the vector field F, and I actually did make this up slightly carefully. Suppose I take the vector field whose components are xz, yz, and x squared plus y squared, and I ask you, what is the integral? What is the flux of F across the boundary of M, where M is points in 3 space satisfying the following equations? We'll say z is between 1 and the square root of x squared. Let me say it this way, where M is the region bounded above by the sphere x squared plus y squared plus z squared equals 2, and below by z equals 1. So this is partly dealing with Gabe's question, in fact. So what does this M look like? So I've got a sphere of radius what?
Square root 2.
Square root of 2, and then I'm slicing below with the plane at height 1. So M is this region that's between the sphere and that planar region on the bottom. So notice this is not a manifold with boundary, officially. Why?
Yes. Doesn't have an orientation.
No, that's not the problem.
It's not an R plus.
What's the boundary of this region?
Why wouldn't it be the circle on the bottom?
What's the boundary of the region in R3 is a three-dimensional thing. What's the boundary of it? There's a disk on the bottom.
And the circle
and
around
the-
it is?
No,
The top part of
the top part of the
sphere.
sphere. So there's a
That's
spherical
not a-
cap union the disk on the bottom. Is that a smooth manifold? No, it's got corners. Right? Right? In profile, we're looking at this, and that is not a smooth curve. It's piecewise smooth, but it's not smooth. So the comment I'm going to make is here that warning sign. M, the boundary, M is not a compact manifold with boundary because the boundary is not a two-dimensional manifold. Right? The boundary is not a two-dimensional manifold, but it's a piecewise manifold. It's the union of two manifolds with boundary. Nevertheless, Stokes applies. So I'm not going to, in all sorts of physical applications, you're going to have situations where you have a piecewise smooth boundary, and we're still going to say the theorem works even though I'm not going to prove it in that generality. Okay? So I'm not asking you to worry about that. Go ahead and apply the theorem.
Pretty much any time a planar region intersects a sphere, we're gonna have this problem.
Yeah, well, anytime you have two
We're
things intersecting,
But aren't, yeah.
considering the entire shape.
you're gonna have a corner. Right?
But-
So the comment here is as long as the boundary is piecewise smooth, the theorem applies. Just like we talked about line integrals on piecewise C1 curves, where you just take the integral on this piece plus the integral on this piece plus the integral on this piece. You can do the same thing here.
Just making sure, if we were to have just the surface, just a hollow shell, and looking at that surface integral, and if
I don't understand.
if
You
we
mean the whole sphere?
instead of like a filled out sphere, if we just wanted to do the top part without including the plane underneath, if
So you mean just the spherical cap here?
yeah, that would be fine, right? With Stokes theorem.
No. I'm gonna get to that. I'm gonna get to that.
So if we're gonna break this into two pieces, how are we gonna do orientation?
Well, so what about orientation? How do we orient a region? If I don't specify otherwise, what's the natural orientation on a region in RK? No, a region in RK. It's the closure of an open set. How do I orient an open set in RK standardly?
Standard coordinates?
What do you mean?
Like X, Y, Z.
Okay, so you, unless otherwise specified, use the standard orientation on R, in this case R3. And then that means that the boundary inherits the boundary orientation. So what's the boundary or the induced orientation? The boundary is what? So it's two surfaces that are each, two pieces that are each smooth. How should I orient them? I'm taking, remember, the unit normal pointing outward, followed by the oriented basis for the surface, should be the standard orientation on R3. So what should be the outward normal? It should be the outward normal. I should orient the spherical cap outward. That's how I would get the boundary of the inside ball. And if I want to do the disc here, how should I orient it? Pointing down, because I want to point away from the inside of the manifold. Right? The manifold is above, so outward pointing means going away from it, which means down. Okay? All right. So how do I do this problem? I'm asking, what's the flux of this vector field outwards across the union of that spherical cap together with the boundary of the disk at the bottom? Obviously Stokes' theorem, so what do? I don't recognize Stokes' theorem because I don't see an omega and a d omega.
But F in the
Omega is
I have to make omega by doing what with this?
F is gravity.
Find the normal and then copy
No.
the area 2 form?
No.
It's like
How do we do flux?
XZ, dy, wedge, dz.
F1.
You just put them in place of the front.
Put the coefficients of f in the standard slots where you used to put
The
the coefficients of the normal vector. Right? So omega should be the flux 2 form associated to the vector field. That's what I was calling eta earlier when we were doing surface integrals. So what do I write down? xz
dy wedge dz.
dy wedge dz plus
Yz dz wedge dx. X squared plus y squared dx wedge dy.
Okay. So what I'm asking for is the integral of omega over the boundary of this region. So, yes, you could do this the way you did it last week in homework by writing it as a sum of the integral over the spherical piece and the integral over the disk, oriented correctly, and just bludgeon it out and do the straightforward computation. Okay, I'll come back and check on you in 45 minutes. Meanwhile, how will the rest of us do it?
We're gonna do a spherical coordinate.
Meanwhile, how will the rest of us do it?
You take d of omega
Take d of it and integrate
over the whole.
over m, over the...
Yeah.
So I'd rather do a triple integral over a region in R3 than I would then do
Surface.
two surface integrals, right? Just like I'd rather do a double integral in the plane over a region rather than doing a line integral. In general. So, what is d omega? Hint, it's not too hard.
Z.
That was before. There will be z dx dy dz plus
It's just gonna be 3z.
z dy dz dx. Well, this is what you got.
Oh yeah.
C dy wedge dz wedge dx plus
0.
0. Now, in case you have not already figured it out, our whole reason for putting this guy in this order is that what happens when I do this?
It's positive.
It's the same as dx wedge dy wedge dz. It's two switches. Okay? So I'm going to get twice z dx wedge dy wedge dz, and so all I have to do is integrate 2z dx wedge dy wedge dz over this region in 3 space. 25 guesses, but the first 24 don't count. What's the best way to do this integral? Probably spherical coordinates, although you could use cylindrical. But remember, at this point, this is in the standard order because I've already told you we're doing the standard orientation on R3. That's the standard order. So I'm going to do the integral of 2z dv, and at that point you just go into automatic pilot back from chapter 7. So if I do this in spherical coordinates, what's dv?
dz dr d theta.
Rho squared.
Wow, sorry, it's cylindrical.
Which of course you could do by pullback now if you parameterized and did the computation. But why take 5 minutes when you know the answer?
D rho.
d rho, d phi, d theta. What's 2z?
2 rho cosine.
Okay. And what are my limits on my integral? Now you have to think.
Theta.
Theta you don't have to think.
You guys will.
Now,
Too much thinking.
thanks Davis. Phi goes from what to what?
Goes to pi over 4. Well, negative pi over 4 is
0 to, so what's this angle here?
Oh yeah, 0.
So what's the best way to figure that out? The height is 1,
And the radius is
the radius is square root of 2.
Therefore,
That shouldn't be too difficult.
49. So pi over 4.
Pi over 4. And now, remember,
Rho, or.
you say to yourself,
So.
take a fixed phi and a fixed theta, shoot a ray out, and it enters where and exits where? It exits at root 2.
And it starts at root 2 cosine b.
No.
Yeah.
Where it enters here and
So
exits
secant-
there.
Secant phi.
Do you believe Reese?
Yeah.
We believe y.
1 over cosine. Secant theta. All right. At this point, I'm going to let you finish the problem. I'm going to do
Should
it.
never have square root of 2 somewhere there?
Nope. Here's the square root of 2.
Oh, it's a 1, yeah.
The height is at z equals 1. Z, you told me, was rho cosine phi, so rho equals 1 over cosine phi. Okay, so finish it. And yes, you're going to have work to practice the stuff, don't worry.
What's the original question?
The original question was, what's the flux of this F out across the boundary of this region? And what we're saying is, I'll talk about the physics of what we're doing here next week, but we've turned it into a triple integral over what's inside. It's coming from taking d of the 2 form. Okay? All right, now I'm going to change the question. And this is, I believe, one of the 23 questions that Dave asked earlier. What if the question had been, to find the flux of F not on all of the boundary of M, but only on the spherical cap. So I'm going to write down S here, where S is the spherical cap.
So we already know the answer to that question.
Yes.
So we could subtract.
Okay, hang on. Let me finish writing. I'll get to it in a sec. The spherical cap, taking x squared plus y squared plus z squared equals 2, z greater than or equal to 1, and I have to tell you oriented outwards as usual. All right, Ken.
So we could do the surface integral on the disk.
Okay, so the point is what we just computed, the answer to 1 gives us this plus something else. Agreed? The answer to 1 is what we want plus the flux across, let's say, D, where D is the disk on the bottom, oriented
Down.
But don't we know there's the same thing?
hang on, where D is the disk on the bottom, oriented downward.
It's almost fair boundary.
So what I know is the answer to 1, whatever it is numerically, is what I want plus this integral over D. So how do I solve for what I want? Subtract the flux across the disk going downward. And let me just remind you that it's going downward by putting a little arrow saying I'm orienting it downward, just to remind you. So therefore, what I want is the answer to 1 minus what comes downward out of the disk, in other words, plus what goes upward across the disk up. So you can start to see some physical stuff going on here. So I'm going to say plus here the integral of what comes in the disk going upwards. So we've got this triple integral that's saying what goes out across the boundary of M. And we're saying what comes out the top plus what comes in the bottom.
So it's this.
Sorry.
So it's like everything that goes out, we're just canceling out the bottom.
That's
We're
right.
also adding what comes
So
in, there's
the answer to 1 is still doing this triple integral, which is saying what goes out across the boundary, all of the boundary, and this is canceling out what comes out the bottom.
It's like adding two other O's on the bottom, pushing it down, kind of just cancel out.
That's right.
Can we,
So the point to Dave's question is you cannot apply Stokes' theorem directly to S. Why?
wait, what you got that?
Stokes' theorem does not apply directly to compute
With S being M or S being D?
an integral of omega over S. S being this piece of sphere.
Yeah, but it,
Why does it not apply directly?
Because S is not the full boundary of
S is not the full boundary of a region. Now, you could try to be sneaky and say, well, maybe I can apply, here's S. S is a two-manifold with boundary.
apply Stokes theorem the other way.
So you might try to be sneaky, exactly as Ken said, and say, S is a compact, oriented, two-manifold
Then we were just talking, it shares boundaries.
with boundary. Hang on, I have a lot of words to write. Can I apply Stokes' theorem to S to compute the integral of omega, thinking of S not as a boundary, but as the two-manifold with boundary?
No.
Only if omega is exact.
Only if omega is exact,
We already know that.
and we already know it's not.
Rewrite.
Rats, we would need omega equals d of somebody to use the integral over s of omega is the integral of a d of somebody would then give me the integral of the somebody over the boundary. But since omega is not exact, I can't do it that way. How do I know it's not exact, Cameron?
Because it's not closed.
Right. In order for omega to be exact, it would certainly have to have been closed. D of it would have to be 0. We've already seen it's not.
So is that now?
So, but we know d omega is not 0, hence omega is not exact.
Is there never a time when we can apply Stokes theorem in like both directions?
You just, well, yes, when omega is exact.
With that,
And then this interval would be 0. Right? D of it would be 0. That's what I can do.
That's really the best case scenario.
Yeah. Okay.
Well, and what we just did for like answer 1 is what we want plus all that. It almost seems like we're not accounting for everything inside of the.
That's this.
Well then. That's, yeah,
This is the triple integral.
Yeah, so that has everything inside of it, but isn't the surface just everything on that surface?
Plus the disk.
And
I'm canceling out the disk.
And this is at the bottom. Surface at the top, everything inside is inside of it.
So this is the sum
Yeah.
of what comes out the top plus what goes out the bottom, and that we computed by doing a triple integral.
Yes.
If I want just what comes out the top,
Mm-hmm.
I want to add back in what came in the bottom.
Okay.
And then I've got it. So how do we do this calculation? So to finish, how do we do the integral of what comes in the disk? How do I do that? Well, it's the integral of omega over the disk oriented upward. How do I do that? Let's make sure you know how to finish the problem. How do we do the integral over that surface of that disk on the bottom? Parameterize it how? No. How do you? But let's look at what omega is before we. So what is omega? How do I integrate omega over d? There's omega. It's all written out there. If I look at that 2 form on a disk that's parallel to the xy plane, what happens to the dy wedge dz and the dz wedge dx? Pulls back to 0 because z is constant on that disk. Everybody agree? So when I do this, it's just going to be the integral of x squared plus y squared dx wedge dy over the disk. And in fact, where this disk is irrelevant. There's no z in there. But don't think I'll always be that nice. Right, so now I just do this in polar coordinates. R squared times
R D
r d theta. Theta goes from 0 to 2 pi, and r goes from 0 to... It is 1. Because you have an isosceles right triangle, right? Because we already decided it was 45 degrees. So the radius is 1. And this one, all of us can do in our head. The answer is pi over 2. So this is saying pi over 2 stuff flows in the bottom disk. That, added to the triple integral that we didn't compute, tells you what flows out the top. Okay? Ready for another example? All right. So far we've done stuff that's very similar to what we've been doing for the last couple of weeks, really. Nothing really exciting. Well, suppose I give you the following question. 3. Let S be the surface that's given by these two equations. x1 squared plus x2 squared is 4. And, all right, it's 1. Just to see if you were paying attention. x3 squared plus x4 squared is 4. So this surface is living in R4. Well, if it's a surface, it's actually exactly in R4. Right? If I had more dimensions, this would have, think back to all our implicit function theory and stuff. I have 2 equations in R4, that cuts me down to a surface. If I were in more variables, it would have higher dimension. So I have a circle in the x1, x2 plane, and I have a circle in the x3, x4 plane. And I'm looking at points that are given by point in the first circle, comma, point in the second circle. Do you all see why that's a 2-dimensional manifold? 1 degree of freedom for this point, 1 degree of freedom for this point. So ordered pairs gives you 2 degrees of freedom.
It's not discs.
They're circles. Okay? Now I'm going to ask you to find the integral over this surface of x1 cubed x... Wait, let me double check what I want. Yeah, x1 cubed x3 dx2 wedge dx4. It's actually not a cylinder. What is it looking like? It's a torus. You have a circle in one direction and a circle in the other direction. That's like a torus. But it's sitting in R4. Now, you should complain.
And there's no orientation.
Cameron's complained. So to make the problem doable, I have to tell you how to orient the surface. So, footnote, author forgot to orient surface, provided we orient S by saying, for example, so I need to tell you a point on the surface, and I need to tell you how to orient the tangent plane at that point. This is a connected surface, right? You can get from any point to any other point by a path, because you have a circle here and a circle here. So you should believe, schematically, if I draw you a picture like this, that you can get from any point to any other point by taking a path here and a path here, and just taking the vector that has this and then this is its coordinates. So it's a connected thing. So if I tell you how to orient it at one point, you agree it's oriented. So here's a point that's on this thing. 1, 0, 2, 0. Everybody agree that point's on there? So I'm going to specify that at that point, dx2 wedge dx4 gives you a positive orientation on the tangent plane. Now I'm going to draw you some pictures in a minute, so you'll understand better what this means. All right. So you guys are flipping out a little bit, but that's good because you're going to have homework to do that's similar to this.
That's good.
You could do a surface integral directly. How could you parameterize this surface? You learned how to do that back in chapter 6. How would you parameterize the surface? How do you parameterize the circle? How do you parameterize this circle?
Different variable.
Different variable, right? So you have a cosine sine of s here, and a cosine sine of t here, s and t parameterizing. So you could do that and pull back and do the integral. But obviously I want to do something different. How do I want to do this? Stokes. How should we stoke it?
Aren't those two circles technically
I would
geometry
Stokes
of two discs?
All right, so exactly what Reese is saying is we have a picture in x1, x2 space. We have a circle. And then in the orthogonal x3, x4 space, so this is orthogonal to this in R4. I've got a circle of radius 2. And what Reese is commenting, I believe, is that each of these circles bounds a disk. So what, can you make up for me a 3-dimensional manifold with boundary, whose boundary is this?
Less than equal to.
How many less than or equal to?
2.
What dimension would that be if you filled in this disk and you filled in this disk?
That would be 3, because you like.
Wait, answer the question.
What dimension?
How many, if you fill in this disk, how many degrees of freedom do you have?
1.
2.
If you fill in this disk,
2.
if you do both, 4. That's too many dimensions.
Oh, so you fill in one.
So imagine taking a torus as you think of it in R3. When you fill it in, you're filling in one direction of circle. You're not filling in both. Do you understand what I'm talking about?
You'd be like double filling it. If we
Right. So when you draw this picture, you fill in this circle. You do not fill in the circle that goes around that way. When you fill in the circle that goes this way, that fills up and makes a solid filled in torus. That's the donut that you eat.
So one less than.
So I want to fill in one of these, but not both. And then the dimensions make sense, right, Jonathan?
Yeah, it's 3.
Right? Because you have 2 degrees of freedom if I fill this one in, and you have 1 degree of freedom still not filling that one in. That's 3. Justin looks totally befuddled.
Does it matter which one you fill in?
Great question. No. You get, this is applying the principle we started the day with. You have 2 different manifolds with the same boundary. So you have different manifolds with boundary, the same boundary. When you apply Stokes' theorem, you'll get the same answer, provided you pay attention to orientation.
Are they actually the same manifold though?
No. No.
What happens if
You're filling, you've got different points. So you guys are saying take M to be what we get filling in this guy, but still staying on the surface of the other filled in one on that curve.
What happens if you fill in the
Whoops.
red one is?
So that is different in R4. This set is different from keeping this one equal and putting a less than or equal there. There's two completely different sets.
But it looks.
But they overlap, but they look,
Without orientation.
Wait, do they overlap?
they overlap only on the boundary. They only overlap on the surface.
What happens if, can you do this on a torus and?
I cannot draw this picture in R4 because this thing doesn't fill in R3. Because of the hole inside there. So in R3, there's only one way to fill it in. In R4, there's two ways to fill it in. All right, so take M. Now, what's the boundary orientation going to be? How do I need to orient M so that I get the right boundary orientation on S? This is where it starts to blow your mind a little bit. So you've got. Mhm.
Do we do like that's oriented like upward in the X1, X2
No,
plane?
well,
And then use that property you talked about at the beginning of last class?
so what would be the tangent direction at this point, for example? At this point, for example, I'm taking that point there and say this point here, just schematically. How would I get the tangent plane to the surface? I would take the tangent line to the circle here, that one dimension here, and I would take the tangent line to this circle in that plane, and putting these vectors in the x1, x2 slots, and these vectors in the x3, x4 slots, those would give me the tangent vectors to the surface.
Yeah.
Right? I mean, that would be, for example, taking the tangent vector, so at this point, let's call this point A for the moment, the tangent space of S is the set of all vectors that look like your tangent to the circle at 1, 0. That looks like vectors that have 0 in the first slot and something in the second slot. Right?
That's just the boundary.
And S is the boundary. So you're varying x2, and then you're varying x4. Those are your two dimensions that span your tangent plane. Now, what is the outward pointing normal of S relative to M? So you have S sitting inside M. How do I go outward perpendicular to S but still tangent to M? What vector is going to point me in that direction? So I'm asking you to think about what is the normal vector that's outward pointing to S in M. So schematically, you've got M, and you've got the tangent space to S, and the normal vector is supposed to point tangent to M, but perpendicular to S.
Yeah.
So what direction should I go that will be tangent to this, but perpendicular to this?
Just X1.
102.
I don't want to mess in this plane at all because the way I filled in to make my 3 manifold was in the x1, x2 plane I filled in. So what's perpendicular, what's tangent to this disk but perpendicular to the green line?
That outward,
Just going outward there.
which is
What vector is that?
1, 1. Oh,
Just in the regular plane, what's, it's just the E1, right? 1, 0, 0, 0. This normal should be E1.
Wait, should it be E1, E2?
That's perpendicular to the circle in the x1, x2 plane, pointing out of the filled-in disk.
So it'd be the gradient of the circle at A.
Gradient of the function defining the circle, yeah.
At A.
At A.
Why?
But I'm not filling in the x3, x4 plane. I'm still just going around my circle, so my normal vector only is having to be pointing out of the filled in part. It's not changing in the x3, x4 direction. So this is what my n is. So the rule is, I'm actually going through this reasonably carefully here. And we'll do another four-dimensional thing on Friday, just for your fun. So we're supposed to take what's the right orientation on M. Well, I'm supposed to have that n, the outward pointing normal, and then the tangent vectors to the boundary. This should give me the right orientation for M, if I put these in the right order. So this is telling me what order to put my tangent vectors to S. Go in the E2 direction here, that's going this way, and go in the E4 direction here, that's going this way. This is the vector E2, this is the vector E4. Right, I'm at the point 2, 0 in this red circle. So in the x3, x4 plane, I'm at this point, so again, the tangent vector is pointing in the E4 direction. I'm going to go around the circle so that dx4 is positive. That means I'm going around it this way. dx4 positive means I'm going this direction. dx2 positive means I'm going around this one positively counterclockwise that way. So this should be, this we said was E1, this we said was E2, and this we said was E4. So I want to orient my three-dimensional manifolded boundary so that this is the positive orientation. All right, you'll see where I use that at the last step. What am I going to do when I use Stokes' theorem? I mean, you have a 50-50 chance of getting the right answer, right? You apply Stokes' theorem, you don't think about orientations. If you're on web work, you try it one way, and if it marks you wrong, you put a minus sign. But I'm trying to explain this part.
You're wrong again, you need two.
Well, then your problems were serious. So by Stokes' theorem, integrating omega, this is omega, over S, is integrating omega over the boundary of M, which means it's integrating d omega. Well, what's d omega? Three x1 squared x3 plus, whoops, times dx1 plus
X1 dx1
dx3, wedge dx.
2 wedge dx.
All right, so do you see that this is a sum of two things? I got x1 cubed dx3 wedge dx2 wedge dx4. I give you a hint.
It should be an x3.
Did I do something wrong?
x3 in the first one.
Ah. I'll give you a hint. One of these is 0. Why?
dx3 is a basis, and we don't really know that count.
Well, because it's x1.
What's happening when you do x3 wedge dx4? Do we have a surface in the x3, x4 plane to integrate over? No, we only have a curve. The surface is living in the x1, x2 plane. So if you pull back this form to this M, you're going to look at m, you're going to get 0 because there's no two vectors in the x3, x4 direction. There's only a single direction in the x3, x4
So it
direction.
doesn't have it.
So this is going to be 0. This integral is going to be 0. And now I'll let you think about this, but you can actually now think about how you parameterize m. You parameterize it by a disk in the x1, x2 plane together with a circle in the x3, x4 plane. So this is going to be the integral of 3x1, and notice this is the correct orientation, by the way. That's exactly what we said was the right order. So you're going to get 3x1 squared dx1 dx2 to integrate over the disk here. And then by Fubini's theorem, you can just multiply by the integral of x3 dx4 to integrate over the circle in this direction. So I'm doing Fubini on the disk across the circle and writing it as a product of iterated integrals. So I'll let you finish this up. But the answer comes out 3 pi squared.
I guess that.
Well, I'm out of time, so you're welcome to try to figure it out and ask me if you can't figure it out. You just have